Hi, everybody. Thank you for attending the third section of my lecture. Yesterday, I wrote a proposition that guaranteed that for checking the Weak Lefschetz property, we can only regard the special linear form as you see here. But the ideal must be monomial and our field must be infinite. In the first case, this proposition is proved by Miglore, Mironoic, and Nagel in 2010, and then in finite case, proved by Landquist and Lisa Nicholson. Yesterday, some people text me to the proof of this proposition. So I write down and I want explain a little about the proof, strategy of the proof, because it's not so difficult. And then I start the third section. So I is a monomial, Artinian monomial ideal, and our field is infinite. We set A as a question ring R over a mod I, and we regard the linear form, general linear form for L in A1. Then we can assume that our coefficients is non-zero and an is equal to 1 because our field is infinite. So we construct a new ideal J that is that the generators is that generates by the generators of minimal generators of I, previous ideal, and in one variable less than our ring by substituting this relation, we said xn is equal to the linear combination of the other variables. So it is easy to see that our mod I is isomorphism with S mod J. Each monomial of J, as you see, is this form because we substituting xn with a1 x1 and up to an minus 1 xn minus 1. Now we can replace it by a1 x1 j1. Only we multiply the coefficients, and due to the multiplication of our coefficients is non-zero, it's possible. So we can define another isomorphism that our variables get the variables to ai xi. Then also we have we see that Hilbert function of a over la is equal to Hilbert function of a over our linear a. So we can deduce that the Weak Lefschetz property can hold for this special linear. Okay. Now I start the third section that is about SLP, section 3, Lefschetz properties. In Lau codimension. So for the codimension, in case of codimension 1, we don't have anything to prove because the ideals are principal and it's SLP and WLP, both of them are hold. For in case of codimension 2, we prove that they are has WLP in infinite field and also any characteristic, but in for the SLP in codimension 2, only we have this property when the characteristic of our field is 0. And for The other characteristic we have counterexample in this case. Now I start with showing that in codimension 2 we have weak Lefschetz property in any characteristic. The first proposition say that, as usual, let A be AI, summation of AI be a standard graded Artinian ring of embedding dimension 2 over infinite field of any characteristic. Field where K is 0 in characteristic. Then A enjoy or has weak Lefschetz property. So our ring is Artinian graded, standard graded, and for dimension 2. Every time in the Artinian, standard Artinian rings, we by saying that embedding codimension 2, it means the variable, the number of variables. For the proof, we can set A equal to I modulo I such that our ideal I is a homogeneous ideal of the polynomial ring of codimension of two variables. Polynomial ring K X Y. Okay, now we set n equal to minimum degree of f such that f it's in I. M is a minimum of minimum degree of generators of I. So if we regard the minimum degree, then we have dimension as a k-vector space of a m minus 1 is equal to dimension of R m minus 1. Both of them equal to m. And also we can say that m is greater than or equal to dimension aj for any j equal or greater than m. So as a definition of Sperner number of our ring, we can say that m is the Spencer number. Sperner number of A. Now, as you see, K is infinite. So we can write, we can write a linear form as explained the previous proposition, and we have we can find there exists a linear form for say L such that A over L is isomorphism to K x over x n. And in this case, the other multiplication maps are subjective. So WLP for proofness, the SLP for codimension 2, we need some definitions and basic concepts that I write before the theorem. The first definition was for stable ideal, stable monomial ideal, strong stable, and Borel fixed ideals. Definition 3. 2. I defined, in this case, our ring is polynomial rings. And for the first one, stable ideal, the monomial ideal I is said stable if for any monomial U in I, the monomial xi u over xmu b in I for every I less than mu, and mu is the maximum of J such that xj divided to. For the strong stable ideal, again, we have a monomial ideal. Is strongly stable. If for any xj, for any u in I, and index j such that xj divide u, so xi u over xj again be in I for every I less than j. As you compare the definition, it's obvious that the strong stable ideals is a stable ideal, but the converse isn't true, is not false. And I write the examples, counterexample of stable ideal that is not strong stable. Okay, write a very simple example. So stable property, we can reduce stable, but the converse doesn't hold. For example, you can regard I equal to x2, xy, y2, xz, or in k, x. As you see, x is divide xz, but y, xz, or x is equal to yz not in I. So I isn't strong, stable idea. And the other definition is about Borel fixed ideals. We want to introduce the Borel fixed ideals. Third part. Uh, When we want to define the Borel fixed ideal, we need to action from the invertible matrices on the generators of an ideal. So consider the natural action of GL NOK, that is GL NOK, as we know, it's the group of invertible n times n matrix. Okay, fix consider the natural action of GLN. So for example, we regard this action on our polynomial ring by, for example, let's A be n times n invertible matrix in J L N O K and F B and polynomial in R. Then A act on F as F AX1, AXN, where AXI is equal to summation of AIJXJ from I1 to J1 to. Okay, by this action, we want to define a monomial when the monomial ideal is for a fixed type. A monomial ideal I, how R, how our ring is Borel fixed. If G I is equal to I for any G in B that B is the subset of G, L, N, O, K. B is and B is the all of the upper triangular matrices, invertible triangular matrices. And I write the B consists of any invertible triangular upper triangular matrix. Consists of all invertible space active, all invertible upper triangular matrices. And we know that in characteristic K is 0, the Borel fixed ideal and strong stable ideals are solved. For the proof, you can see Eisenbach's book, as I mentioned in the references for this topic. Okay, now I want to write some remark about the special case of monomials. For the generic ideals, also we have the definition. I don't know everybody knows about this special case of ideals or not. And I recall the definition, no problem. So before the remark, I write the definition of initial ideal and also generic initial ideal for our ideals and the other 3, 4. Okay. Let's it's be a term or the on R with respect to x1 greater than x2 up to xn for an ideal for every ideal and ideal of R, the initial ideal that we show with this notion of I is ideal generated by terms, living terms, our elements of R. Terms in with initial of I is equal to initial F or any F in I. Honka in 2003 proved that the Hilbert function are ideal. The relationship between the initial ideal, Hilbert function of initial ideal and the ideal, and it's very useful to proofness in the topic of Lefschetz properties. I defined the initial ideal. Now, for the generic initial ideal, we can also, we need the lexicographic order, and I defined also it. Let denote the lexicographic degree lexicographic over monomials. Monomial ideals for any monomial ideals means that x1, a1, x2, a2, xn, an greater than x1, b1 up to if the non-zero coordinate of this vector is positive. Okay, we define the degree lexicographic. I think it has. Now I want to define the generic, initial generic ideal. Let I be a homogeneous ideal. Then there exists the open Zariski state of G, L, N, O, K, and monomial ideal J of R such that for every G in U, G in our subset, we have initial of Gi is equal to J. In this case, we called J a generic initial ideal of I with respect to our order. So J is, we call excuse me, J, we write J as Gen I with respect to our term order. Now I come back to the remark that from the Concas paper in 2003 about the reduction number, this paper by the name reduction number, and through a very useful theorems about the generic initial ideals and the Hilbert function of this ideal with respect to our ideal. Remark. 2003. The name of paper is reduction number of initial ideal. Let's our people memory. We prove that and JB generic initial ideal of I. He proved that if we have general linear form. So we proved that Hilbert function of R over J and Xn is equal to Hilbert function of R and I and is useful in the next proof, in the next theorem of for the proof of SLP, strong Lefschetz property for codimension 2. Okay, and also he proved that the dimension as a K-vector space of R over I and L ideal generated by I and L is less than dimension of R and J. And if I is Borel fixed ideal, then we have generic initial ideal of I is equal to I. Because I think we have this definition. In this case, when we write about the generic initial ideal, when our ideal is Borel fixed, then GI is equal to I. And also we can write for, and it's happened for any term order, for any term order. Indeed, we can choose and take an element there. Take the element G in the GL NOK because it is a Borel fixed and we can choose an element that acts on our ideal as equal to I. We can take the element G G N O K, and such that action in equal to I, generic initial I, as I said in the third case of the definition. As an element for a subgroup of GL and K. Okay, we found that the Hilbert function of our generic initial ideal and generated by Xn is equal to Hilbert function and I and L for every general linear form. We compare the dimension and we found that if our ideal is Borel fixed, then the generic initial ideal of I is equal to I. Is there any questions? No. So in this last case, if J if we set the J right, yes, the generic initial ideal, then J is Borel fixed. And in the next lemma, I want to show that when R ion as our module, our quotient module, then our quotient ring has weak Lefschetz property, then also we can say that Xn also is the Lefschetz element on R modulo I. Okay, our lemma. Let I be stable or Borel fixed. Then R ion has weak Lefschetz or strong Lefschetz property if and only Xn is weak Lefschetz or strong Lefschetz element of proof. We define two invariants. One of it is called CL, J and K is equal to dimension of I colon ideal of I L K J and also alpha J and K that equal to minimum of dimension of J unit component of I and R minus R J plus K R I. Generally, always we have CL, J and K is greater than or equal to alpha J or K. If R ion has Weak Lefschetz property, then the equality holds if R ion has Weak Lefschetz property. So Cl J1 is equal to alpha Jn1. If R ion has strong Lefschetz property, the equality holds for any k greater than 1. In the case that Weak Lefschetz property, we have the equality, and we regards two cases. If in this case, in the case that Weak Lefschetz property, the equality holds for k equal to 1, and we regard two cases, stable or Borel fixed ideal. For the first case, if I is Borel is stable, then we have nature of I over x over r xn is equal to I animator of I L K subset of it, because for example, let's we show this subset by show that an element in the other side. Let J be an element of polynomial of x and k, then j, x, and k is belong to I. So for any I less than n, we can divide it g, x, n, k over x, n, x, x, I, j, x, n, k over x, n is equal to xi, j, xn, k minus 1 is in I due to stable, because I is a stable ideal. So we can, because L is a linear form, L is linear form, so L power k can be expressed as the multiplication of monomials such the summation of multiplication of monomials such x1, x2, xn, x. For example, we can write I1, I2, IK such that C is in K, and I1, I2, and IK belong to 1 up to n. So we can divide every monomial in I by the same way, by subtract all of the variables. So x1, x2, x8 is replaced by also in I because xn can be replaced by other variable, variables. So we prove that we start with G in this column ideal, and by showing that all of the elements is in LK, so G is I column ideal LK. Okay, now we can deduce the dimension of I colon xn is less than dimension I and colon ideal of I and LK. This element, we call this element with CLJK. For K equal to 1, we can consider it and show that the C means that C, XN, J, and L and K is less than C, J, CL, J, and K. And also we have right over here for C all the equality because for the first time I write alpha JK is less than C XL JK and it is less than CL JK and it is equal to C alpha JK. So we have the equality. We can saying Xn is a strong Lefschetz property in R, strong Lefschetz element in Ri. Now, for the other case, when we have I Borel fixed, let I be Borel fixed either. In this case, we can write if this ion has weak Lefschetz property or respectively strong Lefschetz property. We choose an element Lefschetz element. Then the open set of SCH throughout we can write has the Weak Lefschetz, yeah, the elements are R1 Yes, because our linear form is in R1, such that there exists our subset, uh, such that is the weak or strong Lefschetz element. And U intersection with Bn, Bxn that equal to summation of I from 1 up to n, such that an is non-zero, is non-empty. Because it is Borel fixed, and Bxn is the subset of GLN with invertible upper triangular matrix. We choose G in Bn with G minus 1 Xn Bn U. Uh, this element, because it's in U, it's weak Lefschetz or strong Lefschetz element on R over I. So Xn is weak Lefschetz or strong Lefschetz element on R over Gi. But Gi is equal to I due to Borel fixed property, and the proof is complete. So in the case that Borel fixed or stable ideal, we can say that our ring has weak Lefschetz property or strong Lefschetz property if and only if Xn be an Lefschetz, weak Lefschetz or strong Lefschetz element on R mod I. Now, in the next proposition, I want to prove that if we have an ideal, uh, the residue field, the quotient ring RIOM has a weak Lefschetz property or strong Lefschetz property if R over generic initial ideal has the property. Let's see. I introduce generic initial ideal and it's not need to write again. With respect to reverse lexicography or then our modulo I has weak Lefschetz property or strong Lefschetz property if and only R modulo J has WOP or WP. For proof, let's we choose and linear form, general linear form in R1, and we have we introduced two invariants, one of them the LJK, it's the dimension of R over I and LK, J component, and gamma, also the gamma JK, is the maximum of 0 and dimension R modulo J plus K minus dimension J. It's deduced from the exact sequence because we if L is a weak Lefschetz element for the multiplication map, we can write R ion R plus J plus K J. We can write for every J and K, J and N and K greater or equal to 1. Normally, we have the L is greater than gamma J, the L, J and K is equal or greater than gamma J and K. Now, if L be a weak Lefschetz or strong Lefschetz element, for the weak Lefschetz element, for K equal to 1, the equality hold, and for strong Lefschetz element, for every K, we have the equality. And we use the definition and proceed by our previous remark about the Hilbert function, our ideal and generic form, the results by the Concas paper. Okay. Let L is weak Lefschetz element. So the L, J and 1 is equal to gamma J 1. For all J, also by remark, I think the number is 2, 3. We have Hilbert function of R over J and Xn is equal to Hilbert function of R, I, and L. For general linear for L and R. Okay, we show that we have this equality for Hilbert function, and by the previous lemma, we have that because Xn is the L is a weak Lefschetz weak Lefschetz element, so Xn also is a weak Lefschetz element on generic initial ideal of I. By previous level of J as weak Lefschetz property because R over J and Xn as weak Lefschetz property, and by the previous proposition we have the equality. For the proof of strong Lefschetz property, for a real point. For the strong case, the strong Lefschetz property, the equality hold for every K and every J. And also we have if L has strong Lefschetz property, then DL J and K is equal to gamma J and K for every J in N and K greater than 1. Also, we have initial of Gi plus xn power k is equal to initial of Gi plus xn k for every k greater than 1. It has an easy proof in Eisenbach's book. You can find it, I think, in the commutative ring of Eisenbach's book. You can find the simple proof. So we can write Hilbert function of R over J and X and K is equal to Hilbert function of R, I, and L. This complete verb. G is the element of GLN, GLN and K. J is a generic initial ideal in this case, because we see that the Hilbert function of generic initial ideal and the ideal is equal together. In the remark, I write down it. So we also can prove that if our ion has the weak or strong Lefschetz property, we can prove that our initial ideal also has the property. But the same proof, and so only I write the proposition without the proof, because the proof is the same. Proposition 6336, our ion has or SLP if and only if R over initial I or strong Lefschetz property. We use this relation that I write in the remark is R over I and L J is less than R J and L I, where J is initial and the other stages are the same. Okay, after the proving these propositions and lemmas, I am ready to prove the strong Lefschetz property in codimension 2 and for the characteristic 0. Let R equal to K 1 be the polynomial ring. Into variable over Yeah. K with characteristic K is equal to 0, then every Artinian algebra A equal to R over I with standard breeding has strong Lefschetz property. For the proof, the strategy of the proof is to regard our ideal as Borel fixed ideal, because as you see in the previous lemmas and propositions that it is sufficient and necessary condition for being the Rion strong Lefschetz property. So we reduce the proof to the case that our ideal be Borel fixed ideal. Okay, proof. And suppose that I is a Borel fixed ideal in our ring. We have the characteristic of K is equal to 0. So ID, the components of I can be generated by consist of monomials. I can write ID generated by xt, x minus y, x, y, t minus 1, and y. Okay, we can regard ID as a generator by this monomial, and that has Hilbert function H0, H1, and HS. With this Hilbert function, let's be Hilbert function of R over I. This is unimodal. Because as you see, the degrees is obvious that it is unimodal, and can regard two cases. Assume Hi is less than Hi+ D, then the Hilbert function is H0 H1 H2 H3 H4 H5 H6 H7 H8 H9 H10 H11 H12 H13 H14 H15 H16 H17 H18 H19 H20 H21 H22 H23 H24 H25 H26 H27 H28 H29 H30 H31 H32 H33 H34 H35 H36 H37 H38 H39 H40 H41 H42 H43 H44 H45 H46 H47 H48 H49 H50 H51 H52 H53 H54 H55 H56 H57 H58 H59 H60 H61 H62 H63 H64 H65 H66 H67 H68 H69 H70 H71 H72 H73 H74 H75 H76 H77 H78 H79 H80 H81 H82 H83 H84 H85 H86 H87 H88 H89 H90 H91 H the multiplication by YD from RIOM I plus D is injective. If HI is less than HI plus D, then this multiplication is injective, because if we choose a monomial in R ion I, then YDM is in R ion I plus D, because the degree of M is I and I plus D. So this is the injective. We can say M is the monomial of R ion from the last. So if regard M is the monomial of R ion I in the last, then MYD also multiplication by YD also is the monomial of R ion I plus D. Now we assume that for this case we have injectivity. Now we assume that HI is greater than HI plus D. So we must show the surjectivity. Then suppose we choose a monomial and in R in this I modulo I plus D. Then we must find the monomial in the other side with the monomial from the last. Then monomial I. R modulo I from the last is we start with HI is greater than or equal to HI plus D. Then we have a monomial in this case, and so from the last, the monomial from the last is exists because HI is greater than HI plus D. So we can write it, for example, we can name it N we let it be n. So Mn is belong to R. So if we write n, so yd n is equal to n. And it's proved the surjectivity for this case. Okay. So the multiplication map yd is surjective. We prove that if I is a Borel X ideal, then strong Lefschetz property holds. Okay, in this case, we prove that our ring has strong Lefschetz property when our ideal is Borel fix. Now we set the general case. We regard the general case. But also we mentioned that the characteristic of our field is 0. In general case, we have the fact that the generic initial ideal of I is Borel fixed as we have a remark. And also by the remark, Conca proved that the initial of I yd is equal to initial I over yd for every d. Also, we can find it, as I said before, in the previous proof, in Eisenbach book, you can find the proof. And where in here R is, Y is a least variable, last variable in with respect to the graded reverse lexicographic order. Now we have the same Hilbert function for our ideal with the generic initial ideal. So we have y as a last variable with respect to reverse lexicographic order, and we have the Hilbert function of R over generic initial ideal of I is equal to Hilbert function of R over I. And strong Lefschetz property is characterized by H vector by Hilbert function of H vector of I over y dA for D1, 2. So general case can be reduced to this reduced to the case of Borel fix. And the proof is complex because in general case also we show that it's reduced to Borel fix idea. Everybody, if you have questions. In as you see for characteristic 0, we have this theorem that our codimensional ring has with strong Lefschetz property, but in characteristic, the other characteristic with positive characteristic, we don't have, we doesn't have this property. For example, you can regard I XP YP in variable, then our ion, our mod I fails to SP. We can also uh, generalize it to high codimensions greater than 3. We come back to this topic in higher codimension. It's section 4. Tomorrow we will discuss about the codimension 3 and higher than 3 and bigger than 3. Okay, now I want to introduce two tools for studying the Artinian Gorenstein algebras. The first one is inverse system, Macaulay inverse system, and the other one is Hessian matrix, higher Hessian matrix. Today I want to start the general case of Macaulay dual, matrix Macaulay duality for general case, and then tomorrow I restrict our attention to the case that our characteristic is 0. So I start the definition of definition of inverse system. Okay. Okay, for firstly, I must recall that for every vector space, generally we define the dual vector space, and we want to show it's also can happen for the rings and modules, and we want to extend this property, the dual property for modules and rings. So there we want to define the graded dual of the polynomial ring in the first step. Recall the notion. I recall the notion. The notion of the dual of dual for and k vector space. For the k vector space, we have for the first definition, let V be a P and K vector space. Its dual is we show by V star is a form of V homomorphism from V to K over our field K is equal to every uh, vector linear functional from V to K such that V is K linear. This is the vector space of K linear transforms from K from V transpose on V. Okay. Now we want in if in linear algebra we know that if V is a finite vector space, then we can write V is finite vector space. So we can write the dual of our vector space is the isomorphism with V as a vector space. This is isomorphism. Now we want to extend this concept to the ring and modules. Mhm. So let's our ring be graded. Okay, the second definition, we call it divided power. Algebra. Let R be K, X1, Xn, polynomial ring. And R star be all we define R star as from of R and K in graded case over K. If we write R as graded case, then we can write 1 over K and R. Okay, that is isomorphism to R and K. Yeah, 1 over 6. It's B, the dual graded of R. In the graded case, we can define the dual graded of R as R star. We can also use a standard shorthand for every monomial. For example, I can write for every monomial, we can say if A is equal to, as a vector, A in Z n for n greater than 0, then XA, when we write XA, it means that X1, A1, Xn, and power A, n. And the corresponding monomial in R star is, so if XA is in component D, we write X bracket A for the functional in RD, in R star. So in R, we use this notion, XA, and for R star, the dual component, we regard this notion. Now we want to define the action, derivation action. And in this case, when we want to write the functional, we can say that this is XA for the functional in R star D on R D when XA because in this summation from our Ri to K, we want to define XA goes to 1 for the our one to 1 to 1 as and all other monomials in already to C0 and all other monomials goes to 0. We also can show that we make the convention from now on to write xi for the dual xi in R star 1. It means xi is equal to xi1 for the in I is 1 and the other coordinate are 0. Okay, as a vector space, we can say R star is isomorphism to a polynomial ring in variable x1, xn. So we can write R star x1, xn. Okay, we can now regard R star as a divided power algebra. R star has divided power algebra which we can prove, we can define the action for this reason. We call x bracket A and divided module, divided monomial, and we write R star is K x1, xn divided power. R can act on R star as contradiction by contraction, which we denote by that defined by A acts contraction XB is equal to XB minus A if B greater than A, otherwise is 0. A is 0. And we can extend this action to all of the monomials. We can extend linearly to all of monomials in R and R star. This action of R on R star gives a perfect pair as we defined in Poincare duality, perfect pairing of vector space. RD, uh, RD star to K for any degree D. Here we define the dual polynomial ring as you see, and then we define an contraction acts on the R on R star as you see, and we have the perfect pair. Now we want to show that we can define some subspaces. Suppose U be a is subspace of R G. We define U as all G in R star G such that F is act on G equal to 0 for any F in U. Macaulay introduced the inverse system of an ideal I of R by I inverse is equal to annihilator of I over R star is equal to the j's from R star such that f at j is equal to 0 for any f in if our ideal is homogeneous, then the inverse system as of I can be constructed by our util, and we can write. So if I homogeneous, uh, the inverse system of I inverse constructed with I inverse in degree d is equal to u. U is substitute, yeah, it's equal to I over d. We have this equality if our ideal is a homogeneous ideal. Now we want to show that R star is has a R structure as module, and we write the multiplication of R star. So R star can equivalent with can be equivalent with a multiplication which makes it into a ring. And define the multiplication of R star as suppose A, B, A1, A up to AN, and B, Bn, and Zn, then we can the multiplication in R star is defined by x A, x B is equal to, oh, sorry, equal to A plus B, x A plus B, where A factorial is equal to AI factorial, and also A, choose A from A plus B is equal to multiplication AI plus BI, choose AI from AI plus BI. With this multiplication, R star is a ring. We can show that it is a ring with this multiplication. And we can also extend this multiplication to all linearly to all of the elements in R star. And if we set XA is equal to 1 up to n multiplication of the variable, then we can write XA is equal to a factorial x bracket a. We have also this relation. If we set, we can deduce that we can write XA in terms of x bracket a. I must say that in characteristic 0, R star is is the same as polynomial rings, and in our case we need the case that our field is characteristic 0. So we can stop here, and tomorrow I proceed this inverse system for the case that our characteristic is 0. Please, if anybody have questions, can ask. Thank you for your attending, and bye.